My name is Aslan Askarov, and this is a joint work with my collaborators Mohammad and Andrei. This work is about information flow. One of the basic notions in information flow is that every piece of information is associated with a security class. Information may move from one class to another, and we use a flow relation to specify when a move is permitted. With many security classes, it is often assumed that the flow relation is transitive. The argument for transitivity goes back to the 1976 paper by Dorothy Denning, where she writes that without transitivity, the flow model becomes inconsistent. Note that this argument assumes that when information is moved between classes, its prior classification is lost. Transitivity of a flow relation is a convention in a large body of work on information flow, yet in certain settings, in particular when security policies are specified in a coarse-grained manner, transitivity may in fact be undesirable. Here's a case for non-transitivity of a flow relation from the CSF 2020 paper by Yi Lu and Chen Zhang. We consider a system with three components, Alice, Bob, Charlie, where Alice permits Bob to read her data, but not Charlie. Bob permits his data to be read by Charlie. Here, if Bob's component sends anything to Charlie, it must be that only Bob's information is sent and not Alice's. Let's look at an example from the same paper where we have example code for each of the components. If we trace the execution of this program starting from the call to method bob.receive, we see that this method simply copies the value Alice data to variable bob.data1. This is allowed. If we look into the now method bob.good, this one copies the value bob.data2 to Charlie's component. This is also allowed. Now let's look into the execution of a method bob.bad. This one copies the value bob.data1 to Charlie.data, but at this point bob.data1 contains the value of Alice data, and this violates our policy. Lu and Zhang approached this problem by dropping the transitivity requirement from the flow relation and proposing a new definition of non-transitive non-interference. They design a specialized type system to enforce non-transitive non-interference and show that it's sound. This methodology makes a lot of sense, but because it relies on a non-standard type system for enforcement, it also poses the question of whether any of the traditional information flow techniques can be leveraged for tracking non-transitive policies. In this paper, we answer this question affirmatively. Indeed, standard transitive information flow machinery can enforce non-transitive non-interference. We accomplish this in two steps. Step 1 is a lightweight program transformation, a pre-processing, if you will. And step 2 is a lattice encoding, where we address the issue of dropping the lattice assumption by bringing in power lattices. This is based on the insight from complex label models such as DLM and DC. Let's look at each of these steps closely. First, we observe that parts of the component state, such as Bob data 1, are used as both data sources and data sinks. In the first step, we rewrite the program so that source and sink usage is isolated. In particular, all occurrences of variables such as Bob data 1 is replaced by three variables: the original one, but now this one is only used for the initialization, a dedicated sink variable that only contains the final value, and a temporary variable that's used for the intermediate computations throughout the bulk of the program. We add initialization and finalization in a way, passes in a way that makes the rewritten program semantically equivalent to the original. Here, let me show you an example of a program after the rewriting. Just check out the initialization and finalization passes. And the bulk of the program here is in line for the reader's convenience. So, this is step 1, the rewriting. Now let's look at step 2. Here we observe that a non-transitive flow relation between, say, A and B is really about permitting flows from A's source to B's sink. So in this step, we represent each component by two levels in a power set lattice. What kind of power set lattice? Well, that depends on the non-transitive policy that we are given and mainly on the number of components in that power set lattice. So if we have the policy for our running example, the power set lattice that we will construct looks like this. The ingredients of this lattice, the elements here, correspond to security classes that can read source data of components. So element x1 to xn corresponds to a security class that can read data of components x1 and xn. And element bc corresponds to a security class that can read source data of components b and c. Next, now we need to identify how we can map the source and sink levels for each of the components to this power lattice. For the source levels, this is relatively straightforward. We just map them to the singleton elements. For the sink levels, we need to look into the non-transitive policy. In this example, for a sink, component A does not flow to any of the other components, so we map it to the singleton. For B sink, we map it to the element A and B because component B can read data from both A and B. And similarly for C sink, we map it to the lattice element BC. So this is the essence of step 2. Combining step 1, the rewriting, and the lattice encoding with step 2, we get the theorem. The theorem says that given a program and a non-transitive flow relation, there is a semantically equivalent program and a transitive flow relation such that non-transitive non-interference for the original program holds if and only if transitive non-interference holds for the modified program. What is this theorem good for? Well, it means that we don't need to use a dedicated type system or our dedicated enforcement mechanism for enforcing non-transitive non-interference. We can just use what's out there. For the formal calculus in the paper, we show that the flow-sensitive type system of Hunt and Sands from 2006 is strictly more permissive than the specialized type system of this SF paper. We furthermore demonstrate the practicality of this approach by working out a few case studies on top of a Joanna information flow analysis tool for Java. Here you can see the lattice model for the running examples that we provide to Joanna as part of a configuration. Now, some of you may observe that the power set lattices may be expensive to represent, and in the paper we also explore alternative encodings. One is a source-to-sink lattice encoding, where we start off a partial order consisting of the source and sink elements for each component. We add flows between sources and sinks for each component, and then we add flows between source and sink elements based on the non-transitive policy. The resulting partial order may not be a lattice, so we use Dedekind-MacNeil completion algorithm to obtain a lattice. Finally, let me show a minimal lattice for this example that we constructed manually. Observe in particular how C source and C sink are positioned in this lattice with respect to B source and how they are collapsed. To summarize, this work was motivated by Lu and Zhang's paper on non-transitive non-interference for coarse-grained information flow. We expect that there may be other applications of non-transitive policies. In this paper, we show how to use existing information flow machinery to enforce non-transitive non-interference through program rewriting and lattice encoding. Interestingly, minimal lattice encodings remain tantalizing. This concludes the presentation. You can find the paper details at the URL below, and I'm looking forward to your questions.